All right, let's take another look at an example involving work this time and energy. So we have a box initially at rest and that's beginning to being pushed across the floor. We're going to calculate the velocity of the box after it's been pushed for 6 meters. The box is still moving at this point. We're just looking at a snapshot in time of after 6 meters of being pushed at a constant force, what is the velocity of that box. So let's take a look right now. Our initial state is before the box has been pushed. So while the box is initially at rest on the ground, does it have either kinetic or gravitational potential energy? The answer is no, it doesn't have either one, right? So we're going to cross them out. No kinetic, no motion, no kinetic, no gravitational potential. It's on the ground that we've defined to be a height of 0. So no energy at the beginning at all. Then let's think about our system here. Let's call our system just the box. In this case, we could include the Earth in our system, but it's not necessary. We're not considering gravitational potential because there is no height change. So now that we've covered the initial energy and our system, before I think about the work done on this box, I'm going to take a look at the final energy state. So I know that after the box has been pushed for 6 meters, the box now has some velocity. So it's going to have some kinetic energy. I'm just going to say that there are 3 packets or 3 chunks of kinetic energy, if you will. I'm also going to say that there's no gravitational potential energy because the box doesn't have any height change. And we're going to say there is no thermal energy either because we are not including the floor in our system. If we were to include the floor in our system, we could consider thermal energy instead of work, but I'll take a look at that in a moment. For now, we don't have any objects in our system that actually have thermal energy, so we're just going to think about the box for right now. So if I have 3 packets of energy after, right, and I had none before, that means that somehow the box had to get 3 chunks of energy. And that's the work that was done on that box, right? So I know that that box is being pushed across the floor. There is positive work done because the force applied is in the same direction as the displacement. So cosine of 0 there will be 1. It'll be positive. So therefore, I can show an arrow. I'm going to show a big arrow coming in here. I'm going to show a big arrow, a boxy arrow, if you will. And this is going to be positive work by the applied force. That's the work coming from the pushing force, okay? So that's going to be, let's see here. We also have to consider the work done by friction, right? So I know that this, let's say there's 4 chunks of energy done by the applied force coming in. So that's going to be positive work, right, because it's coming in. Then I know there's also friction, right? Friction's also doing work on the box. And the work done by friction, as we saw before, was negative. And so that'll be an arrow coming out of the circle, the system. And I'll just show one chunk here. This is going to be negative work by friction, right? So if we have like a positive 3 chunks and minus 1 chunk here, then positive 4, right? That's why we did 4 chunks. So that when we subtract 1, we're going to have 3 left over. So that's just one way of accounting. Again, this is not quantitative. We're not saying that the work done by the applied force is 3 times greater than the work done by friction. We're just trying to account for the relative amounts of energy, okay? So what I can do now is I can write out my energy equation now that I've accounted for my initial energies, my final energies, and all of the works done on this box. So what I'll say is, right, there's nothing here in the initial state. This is all 0, so I'm not going to put anything here. And then I'll say the positive work done by the applied force, right? And then I'm going to add the work done by friction here as well. The reason I'm not making it negative yet is because the work done by friction is already negative. So I don't want to subtract it because then if I plug in a negative, I'll get a positive. So I'm just going to add all the works together. And then later when I plug in the values for the work, or if you know the work done by friction is negative, you can plug in the numerical value. We don't want to make it double negative, right? And so that'll be equal to, right, both of those works together will be equal to the final kinetic, or the kinetic energy at position B. All right, so now that we have our energy conservation equation, it's just a matter of plugging in the equations for work for both applied force and friction force, and the equation for the kinetic energy of the box at position B, which again is that 6 meter point. So we've actually solved this problem in a previous video. So I know that the work done by the applied force is just going to be equal to the force applied times cosine of, in this case, 0, because the applied force is in the same direction as the displacement, times that displacement value, right? And that'll be equal to the, or that'll be in addition to the work done by friction. That'll be the force of friction multiplied by cosine of 180 degrees, because friction will be pointing opposite. This will be the force of friction. That cosine of 180 will make that negative then. That'll be multiplied by that same d. That'll be equal to 1/2 the mass of the box times its final velocity squared. And that's what we're solving for. We're solving for this. So I'm actually just going to rearrange for VB directly before I actually plug in my values. I'll simplify the cosine values, but I'll go ahead and plug in my values afterwards. So I'll say that I'm rearranging. I'll multiply both sides by 2, and then I will divide by the mass and take the square root of both sides. So I can say that 2 times the applied force times the displacement plus the force of friction. And that's going to be actually, we can show that as a minus now, because that cosine of 180 we can evaluate, times d. And then I'm going to divide by the mass, and then take the square root of the whole thing to get VB. So I skipped a couple algebra steps there, but to get rid of the 1/2, multiply both sides by 2. To get rid of the m, divide both sides by m. And then to get rid of VB squared, we'll take the square root of both sides to get VB by itself. So this is my final expression then. I can now plug in the values for the applied force, the displacement, the mass, and the force of friction. If you recall from our previous video, the force of friction exerted on the box in this case was 44.1 newtons, and we got that using Newton's second law. So please confirm that for yourself and make sure you understand how we got the force of friction for this scenario. So once again, that's going to be the final velocity. That final velocity at 6 meters displacement will be the applied force here, multiplied by that displacement, minus the force of friction, 44.1 times 6, and all that will be divided by 15 kilograms. Square root of all that will be equal to, it's about 6.7 meters per second. All right, and so what we've just done is we've solved for the final velocity of the box after pushing it with a constant force for a certain displacement, which again is a problem that we would normally have to solve using Newton's second law and kinematics. And we've been able to essentially eliminate that entire process instead by thinking about work and energy. So this represents an incredibly useful way of solving problems that would otherwise be more complicated or in some cases impossible to solve without an energy lens.